Hey all, I hope this finds you well. This is part 3 of the notes for pre-calc final. I've been a little under the weather, unfortunately, but I'm here on the day before to give you one last review session before your final. I posted a key to the practice final. It's on the drive, so please take a look at the answer key to the practice final and make sure you've seen the entire practice final, and make sure you spend some time going over that. But we're going to pick up here. This is where the last video ended. Last video ended kind of finishing the unit circle, so I'm not going to do the unit circle again. We're going to pick up with just trig, evaluating trig values, and some trig graphing. This is what's next. So I think these we did not do. Sine 135, cosine pi, negative pi over 6, and tan 7 pi over 6. To evaluate these, I mean, you're just going to use your unit circle, right? So 135, you would go to 135, you'd look at the y value, it's root 2 over 2, right? For cosine, you're going to look at the x value. If it's a negative pi over 6, that means we're going to go in the clockwise direction, pi over 6, and that is negative 1/2, root 3 over 2. Okay, and then tan, don't forget that the tan ratio is sine over cosine. Sine over cosine is tan. So we go to 7 pi over 6, which is over here, and we're going to do negative 1/2 divided by negative root 3 over 2, because that's the sine divided by the cosine, right? Sine is negative 1/2, cosine is negative root 3 over 2. So we will get, we'll get this. Negative 1/2 divided by negative root 3 over 2. And that will simplify to negative 1/2 times negative 2 over root 3. This is just going to be 1 over root 3. And then we'll have to multiply by root 3 over root 3. So our answer would be root 3 over 3. Okay? That's it. So don't forget that tangent is just sine divided by cosine. When you divide compound fractions, you multiply by the reciprocal, and then you just multiply by root 3 over root 3 to rationalize the denominator. Okay, that is evaluating trig values. Now we're going to do a little bit of inverse. So inverse trig is when you're given the output, or given the ratio rather, and you're basically asking, okay, well, what's the angle? What angle gets me that? So there's some kind of restrictions here. If you just see these and it doesn't specify, there are these implied range restrictions. So I'll talk about those over here to the right. So arc sine, arc tan, and arc cosine. Well, arc sine has a domain from range from negative pi over 2 to pi over 2. Arc tan is from negative pi over 2 to pi over 2. And cosine is from 0 to pi. What this is saying is when we put in one of these ratios, there's technically infinite solutions. You can just keep going around the unit circle, right? If you think about inverse sine 1/2, well, that's at pi over 6. It's also at 5 pi over 6. And I could just add 2 pi to both of these, infinitely, and get infinite solutions. And so that's a bit of a problem. So what you'll generally see is, you'll just see one answer, and that answer is between these values here. So this, absolutely put this on the note card. Definitely note card this, for sure. So let's do some practice problems. So inverse sine 1/2. Okay, you can use a unit circle. When is sine 1/2? Well, it's at these two places. It's at pi over 6. It's also 5 pi over 6, but we're not going to count 5 pi over 6 because it's outside of our range. We're only going to count pi over 6. So this would just be pi over 6. Inverse cosine negative root 2 over 2. Well, okay, where is cosine negative root 2 over 2? It's right here at 3 pi over 4, right? It's also here at 5 pi over 4, but we're not going to count that because that's outside of our range. We're only going to count the 3 pi over 4. So this would be 3 pi over 4. Sine, where's sine -1? Well, -1 happens right here at 270. We're not going to call that 270 though, we're going to call that -90 or negative pi over 2. And then where is tan root 3? That is at pi over 3. Okay. So unless it says otherwise, unless it says give me all the solutions, you're just going to choose the one angle between these that meets this requirement. Does that make sense? So you're only gonna look between negative pi over 2 and pi over 2. You're not gonna go beyond that to find the angle that has an output of 1/2. That's what I'm saying. Okay. Hopefully that's clear. We're moving on. All right, graph and trig functions. So before we get into like the transformations, let's just go over the parent trig functions. And yes, I know you only have limited space on this note card, but you should probably put these down. So we have sine, cosine, tangent, cosecant, secant, cotangent. And it's good to know roughly how these look and like the important features about them. Okay, so how does sine look? Well, sine starts at 0, it climbs up, it comes back down to 0, and it comes back to where it started. And it has a period of 2 pi. Okay, that's the period. And it comes up 1 and goes down to -1. Cosine is very similar, except it starts at the 1, then it comes down to 0, down to -1, back to 0, and then back up to 1. And it also has that same period of 2 pi. So these two are really similar, they just start in different positions. How does tan look? Well, tangent is, don't forget, sine over cosine. So whenever the bottom is 0, you're going to have a vertical asymptote. So you ask yourself, okay, well, when is cosine 0? That happens at pi over 2 and 3 pi over 2. And then in between these asymptotes, we increase. It kind of creates this S shape. Like that. Okay. Let's do cotangent. Let's just go into kind of a circle here. Cotangent is cosine over sine. So it's, it's the reciprocal of tangent. So it's very similar in how it looks, except it's when sine is 0 that we have the vertical asymptotes, and that happens at 0 and at pi and at 2 pi. And instead of increasing between those asymptotes, we decrease between them. So we have this and this. Okay? That is cotangent. For secant and cosecant, those are very closely related to sine and cosine, and they also have some relationship to tan and cotangent. Secant means 1 over cosine. Cosecant means 1 over sine. So in the same way that we had vertical asymptotes here, we're also going to have vertical asymptotes for secant and cosecant. Again, it's going to happen when cosine is 0. And cosine is 0 at negative pi over 2 and pi over 2. Okay? And then in the land in between, in the space in between, we have these kind of mini parabolas that go toward those asymptotes. And then in these points here, like the end of those parabolas, are when cosine is 1 or -1. Right? So cosine is 1 and -1 at 0 and at pi. Right? This is pi and this is 0. Okay? Whenever sine is similar, except it's the asymptotes are at 0 and pi, so they're here and here, but there's the same shape, kind of like how cosine and sine are also the same shape, but kind of just in a different position. Secant and cosecant are the same shape, just in a different position. tangent and cotangent are also very similarly shaped, just position's a bit different and the direction is different. So these are the parent functions, the parent trig functions: sine, cosine, tangent, cosecant, secant, and cotangent. So if you know these, if you have this down, it's really not too bad to do the transformations. So that's what we'll do next. Okay, so we're on graphing trig functions, page 15. Sine 2x minus 1. Okay, well, what's this doing? Well, let's go over some basic transformations here. So if we have a sine quantity bx minus c plus d, a is the amplitude, d is the midline, and then b, well, 2 pi divided by b is the period. Okay, so here, because my b is 2, my new period is just pi. Okay, and then that minus 1 is just going to lower everything by 1. So this one will look like this. But this is pi here, because this is one complete rotation. That's pi. Okay? All right. 2 cosine x minus pi over 2. This one is going to sort of stretch cosine. You know, the amplitude is going to be 2 instead of 1, right? So if you imagine this is before, this is after. It's going to go to negative 1 and go all the way down to negative 2 and up to 2. And this minus pi over 2 is going to shift it to the right by 90 degrees, or by pi over 2. Meaning like that normally you start, cosine pi over 2 starts at the top of the valley, but we're going to have to, everything's going to be moved over one to the right, one sort of quadrant to the right. So it's actually going to start here. So it's going to come up, it's going to look like sine. So we shifted everything a pi over 2. Okay, does that make sense? Normally we'd start here, we shifted it there. So we actually start at the 0. This is still 2 pi here. Sorry about that. Tan 1/2 x. So with tangent, this follows a different rule than 2 pi over b. With tangent, because tangent, the period of tangent is pi. So this is pi over 1/2, which is 2 pi. So this made the period of tangent 2 pi. So we can look at our little graph from before. Basically, instead of being a width of pi, right? This period used to be pi. This is going to stay the same in structure, but we're just going to stretch it to be 2 pi. So it would look like this: negative pi and pi, and we're going to draw our asymptotes, and then that would be our function in between. So again, the main difference here is normally this would be negative pi over 2 and pi over 2, but this is stretching everything horizontally by a factor of 2. So instead of negative pi over 2 and pi over 2, it's negative pi and pi. Okay, secant, cosecant, and cotangent. So secant, 1 over cosine, with that 2 pi, sorry, that 2x in there, that's going to increase the frequency by a factor of 2, or it's going to horizontally shrink it by a factor of 2. So what that would look like is it would be negative pi over 4, pi over 4, 3 pi over 4, right? These would be the vertical asymptotes. Rather than pi over 2. To cosecant x, well, the frequency is going to stay the same. So it would still be every pi. But instead of being at 1, it's going to be at 2 and go up like this. And negative 2. It's negative 2, that's 2. Last one, cotangent x minus 1. So we know what cotangent x looks like from our parent graphs. The only difference here is that instead of sort of intersecting 0 at the x-axis, it's going to go intersect negative 1. Like that. So what I'll say here, guys, is just be ready for multiple choice when it comes to these. You know, not necessarily drawn from scratch, but be ready for multiple choice. Okay. For inverse trig functions, don't worry about these too much, but the form of them, this kind of goes with what I was saying before about the range restrictions. They look like so. Okay, but again, don't worry about worry about the concept of the inverse trig functions, like the range restriction, like I mentioned before. But don't worry about memorizing the graphs or anything. Like don't put this in your note card. You don't need it. Okay. All right. We're continuing on the identities. Okay, so I want to be clear that these are given. Okay, so I'm going to give you these identities on the final. What are they? Okay, so we've got reciprocal quotient. That's just saying that secant theta is 1 over cosine theta, and that cosecant theta is 1 over sine theta. Tangent theta is sine over cosine, right? Cotangent is cosine over sine, right? Or it's 1 over tan, or it's this is 1 over cotangent, right? That's all that. That's all these say, right? Right, and that sine is 1 over cosecant, and cosine is 1 over secant, right? That's what these say. The Pythagorean identity, the one you know, the one you'll be given is sine squared theta plus cosine squared theta equals 1. Okay. The double angle identities. Okay, these are important. We have the sine 2 theta equals 2 sine theta cosine theta. There's only 1. But then we have cosine 2 theta, and that has 3 options. It could be cosine squared theta minus sine squared theta. It could be 2 cosine squared theta minus 1, or it could be 1 minus sine squared theta. Move that up. Okay, so there's 3 options. There should be 2 here. All right, again, these are given to you. Okay. Trig equations. We're doing good. Okay. So how do these work? These are like a combination of, sometimes they use the identities a little bit, but they're kind of a combination between regular equations and these inverse trig that we did before. So what do they have to do with each other? Here we have sine x equals negative 1/2. To undo the sine and just get that x alone, you have to take the inverse sine of both sides, right? And what happens is we take the inverse sine of both sides, that undoes the sine, and we get x equals inverse sine of negative 1/2. Then, to evaluate this, you're just going to go to your unit circle, right? And you're going to say, okay, well, where is sine negative 1/2? Where does that happen? Well, it happens here, right? What you got to remember is, if it's sine, you're looking from negative pi over 2 to pi over 2. You're like, okay, well, it happens here at 11 pi over 6. But that's not 11 pi over 6, remember. That's negative pi over 6. The answer is negative pi over 6. That's your answer. Okay. This one, we divide both sides by 2. You're going to get cosine x equals root 3 over 2. And then same thing, we're going to do inverse cosine both sides. And then the question is, well, where does cosine equal root 3 over 2? And that's just that pi over 6. Okay. This one's a bit similar. You would take the inverse of both sides. This is just root 2 over 2. I just want to make sure that's clear. This is root 2 over 2. You multiply top and bottom by root 2. And so you get the same thing. You get 2x equals inverse cosine of root 2 over 2. That's pi over 4. So that means that 2x equals pi over 4, or x equals pi over 8. Okay? So again, how do I know that inverse cosine root 2 over 2 is pi over 4? I'm using the unit circle. Okay, so I'm just saying, okay, well, where is it root 2 over 2? It's right here. Cosine is root 2 over 2 right here. Pi over 4. And this, remember, because for cosine, I'm looking between 0 and pi. Where between 0 and pi is cosine root 2 over 2? It's right here at pi over 4. Okay, keep going. Same idea here. So this would be 2x equals inverse sine negative root 3 over 2. That would be, it's going to be negative, right? It's going to be negative pi over 3. So 2x equals negative pi over 3, or x equals negative pi over 6. Okay, a couple more here. Sine squared x equals 1/2. Okay, so to evaluate this one, we can't inverse it because it's currently squared. We're going to square root both sides rather. We're going to get sine x equals 1 over root 2, and sine x equals negative 1 over root 2. Remember, 1 over root 2 is just root 2 over 2 once you rationalize it. So this is really sine x equals root 2 over 2, and sine x equals negative root 2 over 2. Where does this happen? Well, this happens at pi over 4 and negative pi over 4. That's when we get root 2 over 2 and negative root 2 over 2. Okay. Next one. This is a quadratic. 2 cosine squared x minus cosine x minus 1 equals 0. You factor this. See how it kind of looks like a trinomial, like kind of like 2x squared minus x minus 1? See that? That's basically what we do. We think of this as an x squared and an x and factor it. So this would be 2 cosine x plus 1. Yeah. And then cosine x minus 1. These two will multiply to get this. So remember, this equals 0. That means that 2 cosine x plus 1 equals 0, and cosine x plus minus 1 equals 0. It means cosine x equals 1, so x would be pi, and cosine x equals negative 1/2. That would be 2 pi over 3. 2 pi over 3. Okay. So if it looks like a trinomial, you want to factor it. All right, last two here. Yeah, this one's pretty straightforward. Move that 3 over and divide by 4, and then square root it. We're going to get cosine squared x equals 3 over 4, and then it'll be cosine x equals root 3 over 2, and cosine x equals negative root 3 over 2, and that would be pi over 6 and 5 pi over 6. Last one here. This is a tricky one. This is definitely a harder problem. You have to use an identity because we have a mixture sort of sine and cosine, and it's a hint to you to convert to all be the same. So cosine 2x sine squared x, I can rewrite that as negative cosine squared x plus 1. And cosine 2x I can rewrite as 2 cosine squared x minus 1. And then things are going to kind of cancel. So the 1's cancel, and then this minus cosine squared x will cancel with one of those. So I'll just have cosine squared x minus cosine x equals 0. So I use the identities from the previous page to do this, if that wasn't clear. I use that Pythagorean identity, and I use this double angle identity to convert this to all be cosine, and then things canceled out, and I ended up with this. So you have cosine x, parentheses, cosine x minus 1 equals 0. That means cosine x equals 0, and cosine x equals 1. That means your answer is R. Pi over 2 and pi. Okay, so those are trig equations. You're solving x. This involves getting that trig, which is sine or cosine, right, as you can see. It could be tan, it could be other trig functions, but we'll keep it sine and cosine. Getting that alone, then inverse sining or cosining both sides. And that's it. All right, we're nearly there. We're getting very close. We're on chapter 10, and then we have some review for the last units, which I'll go over. Okay, so chapter 10. Nonlinear systems of equations. X squared plus y squared equals 9. Y equals x squared minus 3. So x squared plus y squared equals 9 is just a circle with a radius of 3. 1, 2, 3. And then x squared minus 3 is a parabola. So this is what we have. And our goal is to find these 3 points. Okay. So how do we do this analytically? I mean, we can see that this point here is, we can see that 0 and negative 3. We can solve this via elimination, via substitution. Let's do elimination. So x squared plus y squared equals 9, and I'm going to move that x squared over. So we're going to have negative x squared plus y equals negative 3. And we're going to add these together. So we're going to get y squared plus y equals 6. We're going to solve this like a quadratic, set a equal to 0. Y squared plus y minus 6 equals 0. That's going to be y plus 3, y minus 2 equals 0, y equals negative 3, y equals 2. All right, so that makes sense, right? Because this is this solution right here. If I plug that negative 3 back into this simpler equation, you want to pick the simpler one of the two, the parabola, not the circle. We plug in that negative 3 in here, x has to be 0, so this is 0, negative 3. Then if we plug this 2 into this here, we're going to get 2 equals x squared minus 3, 5 equals x squared, x equals plus minus root 5. That, though, this is our other two coordinates. Our other two coordinates is going to be root 5, comma 2, and negative root 5, comma 2. And these 2 points are these two up here. Okay? So that's solving nonlinear systems of equations. Just, you can do elimination and then solve a quadratic. You could also use substitution and take one variable and plug it in for another. Either is fine. Okay, let's do the intro to calculus review, and we will call it there. All right, so limits, graphical limits. Expect to see these, guys. 4 from the right. What is this? 1, 2, 3, 4. Is this 4? 1, 2, 3. Oh, negative 4. 1, 2, 3, 4. Negative 4. 1, 2, 3, 4 from the left. This is kind of a, sort of from the right. That's what it says, from the right. Oh, that is, well, that's this point right here. That is, let's think of 1. I just want to be clear that I wouldn't give you something this weird, but this doesn't actually. This is a D&E, but I would never give you a problem like this. I just want to be clear about that. This is kind of a unique case. Limits of endpoints. Let me change the color of this so you can see it. The limits of the endpoints. There is no, basically you have to be able to approach from the left and the right, and you cannot approach this from the left. That's why this doesn't exist. This is a very unique case, so don't worry about this one too much. Okay, so don't just ignore this. You want to just cross this out. Just ignore that. Limit as x approaches negative 3. That is that 4? Negative 2, that's D&E, right? They do not high five. They do not meet. Let's change this to a little better. There we go. Negative 2 from the left is okay. That is 3. Negative 2 from the right, that is okay. That is 1. Negative 2 overall. Oh, I am. Okay, this is not D&E. This is 3. My bad. I thought it was a limit. I was not paying attention. This is just 3. The limit at negative 2 does not exist. F of 1 is 1. F of 6 is 1, 2, 3, 4, 5. This is undefined. Okay. Limit as x approaches 3, 1. That's a D&E. This one we could say infinity and infinity. You could also say the infinity for this one too. 6 from the left. Oh yeah. So the limit as we approach 6, that is a value. That is going to be 3 and 3 and 3. And then as we approach infinity, it is going to 2. Okay? Alright, so again, they have to meet. They can be open, but it has to meet for the limit to exist. They cannot be mismatched like at negative 2 and 1 or at 3. And to be defined, you take what's filled in. If nothing's filled in at that x value, it's undefined. Okay. Continuity, the conditions. 1, the limit exists. 2, output defined. 3, limit equals output. Okay. So here at negative 3, we meet all the requirements, right? Limit exists, right? Limit x approaches negative 3 is 4, right? F of negative 3 is also 4, oh, oops, here, F of negative 3 is also 4, so right, because these two are the same, it's good. At 1, all right, well 1 is defined, but the limit does not exist. Limit D and E, so it's a no. At x equals 3, limit does not exist. So it's a no. At x equals 6, function is not defined. It's a no. Okay. All right. Limits algebraically, this is where just plug in, right? That's direct substitution. To, if you get 0, 0, factor and cancel. And then try again. Intermediate value theorem. The idea of the intermediate value theorem is that if I'll draw it out. If you have two values, a and so two x values, a and b, and f of a is some number, and f of b is some other number, there must be a c such that f of c essentially is between these two numbers. That's what we're saying. On A, B. Okay. Oh, it must be continuous. Okay. Integrals geometrically, this is just where, like, you know, you add them up. That was the whole idea here. You know, you shade the area and you add them all up. That's it. That's integrals geometrically, right? And if it's below the x-axis, it's negative. If it's above, it's positive. Riemann and trapezoid. Okay, so we have right Riemann, we have left Riemann, and we have trapezoid. Trapezoid is 1/2 b1 plus b2 times h. These two are both like base times height, right? They're both base times height. But the difference is that the height, if it's on the right side, is the right side of that rectangle, and if it's on the left side, it's the left side of the rectangle. That's it, really. Okay? That's all you really need to know. All right, if you have a table, right, 0, 2, 5, 7. This is your x, this is your f of x, 7, 10, 11, 12. Right, if it's left Riemann, it would be 7 times 2, 10 times 3, 11 times 2. If it's right Riemann, it would be 10 times 2, 11 times 3, 12 times 3. If it was trapezoid, it would be 1/2 times 7 plus 10 times 2 plus 1/2 times 10 plus 11 times 2, right, and so on. Okay? All right. Okay, here's some more practice of that. So left Riemann, right Riemann, midpoint Riemann. Don't worry about midpoint Riemann. Just worry about left and right. If it's left, you start on the left side. You go over, down, left, over, down, left, over, down, left, over, down, left, over, down, and then you add those together. If it's right Riemann, it's just the opposite. So it's right, left, down, right, left, down, right, left, down, and you'd add those together. That's it. Okay. Finding the derivative using the difference quotient. So again, I'll give this to you. Here, you take the function that replaces f of x. This is f of x, that goes there. H goes in the bottom, and f of x plus h is found by just plugging x plus h into this. So it's 3x plus h squared minus 4. So that would be 3x squared plus 2xh plus h squared. So we write it all out, we'd get 3x squared plus 6xh plus 3h squared minus 4 minus 3x squared plus 4 all over h. These are going to cancel, these are going to cancel. So it's going to be 6x plus 3h, which is just 6x when you take the limit. Okay? That's derivatives. What does the derivative tell us? It's the instantaneous rate of change. Instantaneous rate of change. This is the output, or the y value. This is the rate of change. Okay. What is the difference between AROC and IROC? AROC is f of b minus f of a over b minus a, right? Pretty straightforward. IROC is not. IROC is f of x plus h minus f of x over h. Okay, that's all you need to know. All right, guys, look over the practice final again. Skim through the notes packet again. No, don't skim through it. Read through the notes packet again. Review some delta if you're a bit unfamiliar with a specific section. No curveballs, okay? Similar to this packet, similar to the practice final. Taking a look at that, okay? Good luck, guys.